Thanks, Harley. So hi, everyone. My name is Viraj Pandya. I'm a Hubble Fellow at Columbia, and I'm very excited to tell you about some work that I've been doing with JWST to constrain the intrinsic shapes of high redshift galaxies. So I'm going to specifically focus on this question: why are early low-mass galaxies preferentially elongated? And I'm going to start with a very brief historical review. So 30 years ago, Hubble discovered that at the faint end, high redshift galaxies are not only typically blue and star forming, they're also preferentially elongated. Kavli et al. At the time coined these things as chain galaxies because many of them are also often clumpy. In the mid-2000s, the Elmer Greens had a very nice paper where the title just tells you the result. As you approach the detection limit of Hubble imaging at the time, these chain galaxies really dominated over the zoo of other galaxy shapes in the early universe. And it wasn't until the early and mid-2010s, with the installation of WFC3 and the completion of large surveys like CANDLES and 3D HST, that people like Arjen van der Wel and David Law were able to really robustly show with large samples that at high redshift, low mass galaxies, say out to redshift 3, stellar masses down to 10 to the 9 solar masses, they really had very strange asymmetric axis ratio distributions, with B over A peaking at about 0.3 to 0.4. And this is not what you see for high redshift massive galaxies, which have relatively uniform distributions of B over A, and you're seeing the rounder things as well. It's also not what you see for low redshift galaxies, for example, in Sloan, where again the distributions of axis ratios are relatively uniform, and you're seeing both elongated and rounder things. So it's been 30 years, and we still don't have a definitive answer for this fundamental puzzle: why are early galaxies preferentially appearing elongated? Right? And so enter JWST. There's been a lot of exciting work in the first 2 years, and some of the stuff that caught my attention is, for example, the discovery of large face-on circular disks with JWST that were just completely missed by HST. Another interesting paper by Brant Robertson, which detected all of these high redshift disk-like things in JWST imaging that were missed by Hubble. And then the thing that really caught my attention is this nice paper by Ferreira et al., which showed nicely that the disk fraction in HST is dropping off dramatically as you go to high redshift, but then the disk fraction, according to their JWST analysis, is much higher at the 40 to 60% level. So all this is very compelling and very interesting, but it really begs the question, what do you mean when you say that you've detected a disk? Right? A lot of these studies, they're using visual classifications of individual galaxies one at a time, or you're looking for exponentially decaying light profiles. These are necessary but not sufficient conditions to say that you've detected disks. And so I'm very lucky to be a member of the SEERS collaboration starting early in grad school. And so when we first got the data in 2022, I remember a lot of us were marveling at how HST, with its 50-hour integrations to look at some of these low-mass, early elongated galaxies, right? You have JWST in less than an hour for the same galaxies. You see so much more substructure. And so we really wanted to ask, did JWST find these missing round face-on dwarfs at high redshift? And so that's the motivation for the paper that I led earlier this year entitled Galaxies Going Bananas. This is really building on work that Haowen Zhang did as a visiting undergrad at Santa Cruz when I was there early on as a grad student. And so we looked at the joint distribution of axis ratio as a function of size, and we noticed that in this plane, the galaxies, for example, in this representative high redshift low mass bin, are really tracing out a particular distribution. And so at larger sizes, these galaxies with larger sizes have biased B over A that are small, so they're preferentially edge-on, and at that fixed larger size, there's a deficit of rounder things. And so when we made this plot, the distribution reminded us of the shape of a banana, and so that is the motivation for the title of the paper, Galaxies Going Bananas. Here's some of the images of some of these elongated low-mass early galaxies. They consistently do look very linear and elongated, right? So some of them do look very clumpy, like the old HST chain galaxies. And our main point is that there's way too many of these kinds of edge-on looking systems compared to rounder, more face-on looking galaxies, which implies if you want to preserve isotropy, not all of these things can just be normal disks seen from the side. So I'm going to now map out a little landscape of possible explanations for this puzzle. The first and probably most obvious thing is, do we still have a bias against detecting face-on disks with JWST despite its improved sensitivity? And, the question really is, for the deficit of galaxies to the top right of the banana, is that deficit real? Are we not seeing those galaxies because they're really not there? Or is there something wrong with our detection pipeline or a sensitivity issue with JWST? And so we did our due diligence. We have a long appendix where we put in fake galaxies into our real Sears imaging, run it through a detection pipeline, and we ask, what our completeness is. And so we actually, down to the stellar masses that we're probing, about 10 to the 9 out to redshift 8, we actually should have seen unreasonably large face-on disks, and we didn't see that in our data. And so I think it's time probably for the field to move beyond this explanation, but it's a good thing to keep in the back of your mind. Another interesting thing is we might actually be seeing some intrinsic 3D geometrical evolution in the galaxy population as you go to high redshift, so that these low-mass galaxies are not starting out like the disks that many of our models, including my own, assume. Instead, they must be significantly flattened along a second axis, so like a prolate ellipsoid that's cigar-shaped, or like this triaxial ellipsoid, which is like a surfboard, or like an oval disk as opposed to a circular axisymmetric disk. And you might think this sounds very exotic, but it's not exotic. We know of things like this in the local universe. They're called bars, right? Bars are triaxial or nearly prolate structures. But when you say something is a bar, you really imagine a bar in a massive self-gravitating stellar disk. And that is not what our high redshift galaxies are, right? We have, instead, our things are high redshift dwarfs. They're dark matter dominated. We don't see evidence usually of a bright or even a faint, in many cases, extended disk component. And so you can call them bars if you want, but they're like pure dark matter dominated stellar bars. And the last thing is the early universe is messy, right? So what if we're just seeing a bunch of mergers in action and or dynamical instabilities, which can lead to these kinds of elongated, clumpy structures? So I have thoughts on all of these possible explanations, but I only have time to talk about really one, and I'm going to focus on the 3D geometrical evolution explanation. So the idea here is that you approximate galaxies as different kinds of 3D ellipsoids, right? So I'm showing you 3 extreme examples here. You got a spheroid, an axisymmetric or circular disk, and then a prolate ellipsoid on the right. And the idea is that a population of ellipsoids of one of these types is going to leave a very unique signature on that B/A versus size diagram. So take, for example, spheroids. No matter which way you look at spheroids, they're going to appear round, so they're going to be at the top of this diagram. Disks are different, right? You're equally likely to observe disks from any viewing angle. So instead, in this diagram, you get a vertical, uniform stripe, a uniform distribution of B/A in this diagram. The third class of extreme prolate ellipsoids are fundamentally different, right? So this clicker, for example, is approximately prolate. You're more likely to see it like this or like this with the long axis in projection, and very rarely when the viewing angle is just right, you'll see it down the barrel when it's going to look like a small circle. And so this distribution for the prolate ellipsoid should remind you of a particular fruit. It's a banana, right? And so that's, we think, the solution to this puzzle, that there is a new class of intrinsically elongated galaxies at high redshift with nearly prolate shapes that we don't really see much of, if at all, in the local universe. So at this point, I'd walk you through my Bayesian analysis. I don't have time for that, so I'm going to skip to the most striking plot, which is the redshift evolution of the prolate, oblate, and spheroid fractions in these 2 stellar mass bins where we are not prior dominated, right? So what you notice here is as you move towards cosmic dawn, right? So cosmic dawn is partially part of our highest redshift interval here. As you move towards cosmic dawn, you see the prolate fraction really starts to become dominant at the 50 to 80% level in our work, which is very striking. And in contrast, as you go towards lower redshift, the contribution of the oblate axisymmetric disks is increasing, which is a good sanity check because in the local universe we do see lots of star-forming disks, right? So, but this possibility that early galaxies are predominantly prolate should really raise questions. How does this fit in with our normal models or normal thinking of galaxy evolution? So let me try to address that in the more familiar terms of the Hubble sequence, which I don't need to introduce, right? We have our spirals and ellipticals and composites, and we think we kind of have an idea of how things undergo morphological transformations and quenching and so on. Here's how the elongated galaxies fit into this. Galaxies, we think, start out elongated because they feel the influence of their environment, right? And then at a certain point, as Avishai Deckel might say, these things undergo gas flows and mergers and dynamical instabilities, so they collapse to form a central spheroid. And it's around that central spheroid that you grow, you have this inside-out growth of the disk, right, via mergers, gas-rich mergers, and gas accretion from the circumgalactic medium, and so on. So what do I mean when I say that galaxies feel the influence of their environment? What I'm talking about here is the fact that dark matter collapses along sheets and filaments. We've all seen movies like this, but I think something that's missing from the discussion is that dark matter halos initially also, we think, start out prolate or triaxial themselves. Okay? And so with my amazing colleagues, Farhan Hassan and Hawen Zhang, we've been going into the TNG 50 simulations to try to test our mental model of this. So along with the slime mold technique for mapping out cosmic web filaments in these simulations. So I'm plotting here sigma fill, which is a proxy for environment. So low sigma fill means that you're forming near a very isolated, kind of like a thin tendril filament, maybe even in a void. And high sigma fill means you're at a node of the cosmic web. So sigma fill is a function of stellar mass in different TNG redshift snapshots, color-coded by the prolate fraction for dark matter halos in these bins. And you can see as you move towards high redshift, it's the low mass things that are forming near these initial filaments that are the things that are that tend to be prolate. And in these simulations, which is just one set of simulations, these low mass, low sigma fill, high redshift regions are also where we find the prolate stellar systems in these simulations that Andre talked about earlier. About a decade ago, Severino, Premack, and Deckel showed that prolate galaxies actually form naturally in the CDM due to mergers that happen along filaments, with the filaments dictating the mergers along a preferential direction, the direction of elongation. Right? And so motivated by this is how I got into this field in the first place. Right? So I worked with my advisors at the time, Joel Premack, Andy Faber, David Koo, Avishai Deckel, to propose in a paper that if this story is true, we should see strong intrinsic alignments between these elongated galaxies as they trace out filaments of the cosmic web at high redshift. Right? And we actually looked for this signal, so we predicted that there should be a booming signal based on Mox with actually an early version of Peter Baruzzi's universe machine, but we didn't see the excess of aligned pairs that we expected in candles. And there's many reasons for this, one of which is that we restricted our analysis to only spectroscopically confirmed galaxy pairs, but we found that there's actually a huge bias against getting spec Zs for elongated galaxies for some reason. So ask me more about that later if you're interested. Last thing I want to zoom past really quick. All this talk of elongation and alignments really also begs the question, what is the role of gravitational lensing, even in a blank field like Sears? Right? So we just wrote a paper with Avi Loeb and some of the Sears architects where we address this. We rule out strong lensing as a really unimportant part of this puzzle, but weak lensing is absolutely key. Okay? Here is the Sears footprint. Every single little square here is a single chip from NIRCam. And in every single one of these chips, we have on the order of 50 to 100 background galaxies. And what we're going to do is we're going to average over the orientations and the ellipticities of these background galaxies in the exact same way the weak lensing people do. And when we do this, if the background galaxies are randomly oriented, this summary statistic, this average complex ellipticity, should be less than 1%. But it's not. You can see there's many, many chips here where this average E is of the order of 10%, which is an order of magnitude above the conventional weak lensing regime. So you can look at some of those trips, right? And you can look at the orientations and alignment patterns, and actually you see really striking things in these JWST NIRCam chips. You see almost like polarization type alignment patterns, right? And these bottom panels here, they show the distribution of that summary statistic, that average E, under the null hypothesis in blue, that these things are randomly oriented. And the red line is the actual measurement. You can see we're way out in the tail, so very unlikely that these things are actually just random alignment patterns. You can also look, you can average over pairs of 4 chips, aka NIRCam modules. And we again see, here's an example of a high redshift, low mass, elongated field, right? Lots of elongated galaxies, and hard to tell by eye, but there's non-random alignment patterns here. And then on one more level of averaging, you can average over entire pointing, so pairs of two modules. Here's an example of a massive subsample where, again, in these two modules, you just see these beautiful alignment patterns that are not consistent with being random. So what are some possible explanations? One is there, even though Sears is a blank field, there could be overdensity at low redshift. We think possibly a protocluster filament. And early on with HST, people would use HST to look for dark lenses in blank deep fields, and so we're proposing that this should be revisited with JWST. In fact, we do find an overdensity of lens galaxies at redshift 0.75, and in fact, it's not a coincidence because it turns out that the first detection of cosmic shear from space was in EGS. And in fact, there was a nice paper by Mustakas in 2007 who found 3 strongly lensed systems just outside of the Sears footprint. And they found that when they did the source lens reconstruction for these objects, they required an extra 10% external cosmic shear in addition to the shear from the massive foreground galaxy to reproduce the distorted shapes of the background galaxies. So interesting, coincidence, I don't know. Another explanation is that this could be the discovery of intrinsic alignments that we're hoping to look for. People have trying to find for the past 20 years or so. So we need more work on this with spec-Zs. And then systematics is another thing, of course. So here we have a very careful appendix where I basically use the stars as a null test. So the stars should not be sheared, stars should not be aligned, and so we check that, and we think we rule out PSF as the cause of the alignments. All right, I can say a lot more, but I'm going to stop here with my summary slide and take questions if we have time. Thank you.
Brilliant. Thanks for that. Share the mics right behind you.
Just a clarification, I didn't quite follow so cosmic shear, of course, exists everywhere. So are you saying that you're detecting more of it than is expected?
No, I mean, we only place an upper limit on cosmic shear. We don't actually try to ascribe what we've detected to cosmic shear. That's going to require bringing in the actual weak lensing people with their complicated pipelines to really try to measure the precise amplitude of it. So we have an upper limit on it, but we don't claim to try to measure the precise amplitude. But there must be according to previous work, there must be some cosmic shear at some level in EGS.
But then what is the conclusion in those fields then? I just didn't quite follow.
So we don't know what the source of the alignments is. There's alignments. And we can't rule out lensing. We can't, it could be the intrinsic alignment scenario, but we're leaving that for future work. Right? So there's ways to follow this up. So for example, if it is shear, cosmic shear, you can decompose these polarization type patterns into E and B modes. And if it's shear, you should not get any B modes. If it's intrinsic alignments, then you should get a lot of B modes. That's an obvious thing to do next. I'm not going to do it because it's complicated, but
thanks.
There are predictions, right, that have been made for the level of intrinsic alignments in the context of contamination for weak lensing.
Mm-hmm.
So have you compared that to, independent of whether you detect the protoclusters in the filaments, we know that we can calculate what the alignments are. So we wrote a couple of papers a long time ago where we estimated that. Have you compared that with these fields? For these fields?
No, we did not compare that. That's a good thing to do next.
Yeah, it's already been calculated.
Okay, interesting, cool.
So I was curious if you could come back to your beginning with Cowie and Elma Green and chain galaxies.
Sure.
In the local universe, because I'm curious how tight of a similar situation you're implying there, given that cosmic filaments today would be huge in cross-section compared to a galaxy, whereas they weren't at high redshift. So it seems like a very different situation.
Yeah, I agree. We don't see these kinds of elongated systems at low redshift. We don't see very many, as far as I'm aware, chain analogs at low redshift. And this could be driven by the changing properties of filaments, right? The universe has expanded considerably since the epoch where we're observing lots of these elongated systems at high redshift. But this is why we're doing the project with Farhan and Hawen to try to figure out, at least in these TNG simulations or other simulations, how are the filaments evolving? Are these galaxies that are elongated actually near the filaments? How are they aligned with respect to the filaments? So, I don't think anyone has the answers, but we're exploring this now.
We have to move on. So let's thank Viraj again.